Hello. Okay, my name is Oswald Mendes, and this is uh, a theorem from Pierre de Fermat, the Diophantine equation x to the 4 plus y to the 4 equals c to the 4 has no solutions. The background that is needed to prove that x4 plus y4 equals c4 has no solutions is the world ordering principle listed here. Um, Proof by contradiction on the world ordering principle using the method of infinite descent divided by Fermat for the case when n equals 4. That's the one that we're looking for here. So basically this is x to the 4, right, plus y to the 4 equals c to the 4. Now it is just sufficient to show that x to the 4 plus y to the 4 equals c to the c squared. And basically theorem 13.1, this theorem we're going to use this theorem 2 on the triplet of positive integers. Is a primitive Pythagorean triplet with y even if and only if there are relative prime positive integers m and n, where m is greater than n with m odd and n even, or m even and n odd, such as, and this is most important, x equal m squared minus m squared, y equal 2mn, z equal m squared plus n squared. Now theorem on the GCD, and I made a little proof of it. So let AB and K belongs to the integers of the positive integers. It's the set of the positive integers. GCD KA KB equal K dot GCD of AB. Basically the constants, you take out the constants. Now here what is important, the GCD when A and B are relatively prime, so the GCD of AB is 1, then A squared plus B squared, so the GCD of A squared plus B squared is equal to 1. And this is the proof follows as this. You can take a look. Alright. And this is here is 1 basically because A is equal to D times K1 and B is equal to D times K2. Lemma 13.3, and this is located on Rosen in 6th edition, page 524. If R, S, and T are positive integers, such as GCD of R is equal to 1 and R is equal to T squared, then we can say that there are integers m and n, such as the R is a perfect square, m is a perfect square, and S equals to n perfect square. So we need to show that the Diophantine equation x to the 4 plus y to the 4 equals z4 has no solutions. Well, the proof is a little bit long, so we need to show we're showing basically in two steps, and then we're done basically. We're using the background knowledge I mentioned here. Well ordering principle, proof by contradiction using the method of infinite descent, theorem 13.1, theorem of the GCD, and the lemma. Now we're assuming that x4 plus y4 is equal to z squared has solution other than the trivial solution, right? Other than 0, 0, 0. Right, now we're saying that without loss of generality, the GCD xy equal to 1. Now suppose that the set A, B, and C is the solution for this equation, x4 plus y4 equals c squared, this one. So we're saying that this is true, right? And we prove it already here, right? This one here. So this is true. Let's prove it. You observe that a squared, b squared, and z is a primitive Pythagorean triplet, right? This is a primitive Pythagorean triplet. it can be shown that if you have a prime number, let's say p, then p divides a squared, and p divides b squared, then p divides a and p divides b. Therefore, here's our one of the conclusions, that this contradicts the fact that the GCD of a and b is equal to 1. Now, the way we explain this is by the method of infinite descent. Now is where the method kicks in, right? So first we need to apply the theorem 13.1. 13.1 again. 13.1, sorry, is the Pythagorean triplets. You need to know this. The x is equal to m squared minus n squared, y, and z. Alright? Alright. So we apply the theorem here. We say that this is equal to this one, as the theorem says, having GCD n equal to 1. Then the solution set will be ABC, right? Of x squared, b squared, and c squared, because we're targeting this equation. If we prove this, and we prove that this has no solution, then that is sufficient to say that the original equation, this guy here, has no solution either. All right. Now where we are right here. Now, first we apply the theorem. Second, we let a squared plus n squared equal to m squared. Basically, use this step is coming from this step. Thus, a and m is also primitive Pythagorean triplet. Hence, apply the theorem 13.1 again. That is how it's called infinite descent method. So we perform first time, we select a squared, b squared, c squared. Now we're doing a second time, and we break it down. The first time we did this, the first, right? The first, the second, first time. Second round, we take again our equations. This one here. We said that the set of solution a and n has a solution a squared plus n squared equal to m squared. And recall that by 13.1, m is odd and n is even. Well, this is key, because since n is even and GCD of m and n is equal to 1, this implies that the GCD m comma 2n. Now, here 2n, why? Because we're saying that n is even, is equal to 1. Since n is even, this fact led us to 1, where b squared is equal to n. Now, this guy here in 1 is right here. Alright? Apply lemma 13.3. This is the first time we're applying the lemma 13.3. Right? And r is equal to n equal. Let's call it. If you apply the lemma, you will notice that r is equal to n, and we call it u squared. Alright? S is equal to m, and we call it z1 squared, because our original equation was a, b, and c. Now we're calling z1, right? Then the lemma says that t squared is equal to r. If r times s is equal to t squared, then r is equal to a perfect square of a number, let's call it u, and a perfect square of another number, s is equal to a perfect square of another number, let's call it z1. That is by lemma 13.3. Where, of course, where u and c1 belongs to the positive set of integers. Now here is some algebra. We call another variable u, and u is 2 alpha, where alpha belongs to c positive. Now, if you square it, look at here. If you square it, you will get this. You will get this, perform the algebra. Now, here from 2, we know that n from 2, n is equal to 2rs. So we plugged it in, cancel out the 2's. So alpha squared is equal to rs, right? So rs is equal to alpha squared, a perfect square. Up to here, we applied lemma 13.3 again. So this is the second time. So we applied already twice the theorem 13.1, the Pythagorean triplets. Now we're applying twice, for second time, I mean, the lemma 13.3 again. So let's call it r equal a1 this time square, s equal to b1 square, where of course a1 and b1 belongs to the set of positive integers, since the GCD of r and s is equal to 1, and GCD of b1, a1, b1 is equal to 1, it follows that this guy, our new equation, will have this form right here, right? M is equal to r squared plus s squared. M is 4. M is equal to c1 squared. So a1 4 plus b1 4 equals to c1 squared, where a1, b1, and c1 belong to the set of positive integers. And GCD of a1 and b1 is equal to 1. Now we have that c1, and this is the part, and we have here, this is important, right? We have here this guy, all right? But look at this, c1 is less or equal to c1 to the 4, and c1 to the 4 is equal to m squared, which is less than m squared plus n squared. And this guy is equal to c. We know why? Look. Right here. All right? So now observe that by repeating this process, so we're gonna do it again, the whole process with this new set of variables. Using the method of infinite descendant, it led us to having this guy. And now is when the process, now we can conclude that we're just flipping the, the inequality. And this guy here, is indeed here, this a strictly monotonic sequence that indeed contradicts the world ordering principle. This is, so C2 less than C1 less than C, right? This guy is strictly monotonic, which contradicts the fact that the world ordering principle at the beginning, when we said that the world ordering principle bounded from below, any non-empty subset of Z bounded from below has a minimal element. So we don't have a minimal element because this sequence is strictly monotonic. So we proved that x to the 4 plus y to the 4 equal c to the 2 has no solution. Therefore, x to the 4 plus y to the 4 equals c to the 4 has no solution either. QED. I'm done. Thanks.